Hi folks, I'm going to get right into it. We've got a thread here on GLP claiming that an asteroid is going to hit Earth in a few days. In fact, we've had a couple threads lately claiming that an asteroid is going to hit Earth sometime this month. And for the most part, they don't provide any coordinates, orbital elements, astrometric data, or anything else that could possibly be verified or refuted. They just claim that they're scientists and they have inside information that says that an asteroid is about to hit us. Well, finally, we've got a post containing orbital elements and claims that in T minus 9 days, this asteroid is going to hit us. Okay, so here are the numbers. Do they mean anything? Well, they do. These are provided in what appears to be TLE format, or two-line element format. Now, two-line elements are used for Earth orbiting satellites. In fact, the format is designed such that it's specific to an Earth orbiting object. For instance, the eccentricity has to be less than 1 for it to even fit within the format, and indeed, this is the eccentricity number right here, 9547277. Well, that translates to an eccentricity relative to Earth of 0.9547277. So that implies that whatever this object is, it's less than 1 relative to Earth. In other words, it's orbiting Earth at the time of this element epoch. Now, the epoch is described here. Normally, you would have the first two digits indicating the last two numbers of the year, 2013, and then the next three digits would indicate the day of the year, and then the rest of it would indicate the portion of the day that the epoch starts on. I have to assume that this is meant to be a 0 at this gap, and it's supposed to be 084, which would be March 25th. But they don't really say. In fact, they kind of botch this up a good bit. I mean, for instance, down here they provide a second set of orbital elements, and there's another gap, and this time we have a 0 for the year. I assume they mean the year 2000, I guess? I mean, it's kind of all botched up. Normally I would take that to mean maybe 0 1 on the day, perhaps. I don't know. It's all just screwed up here. But in any case, this would indicate that it would be the first day of the year, January 1st, halfway into the day. Okay, so they provided the elements again this time for January 1st, even farther from the supposed date of impact. Why? I mean, okay, so let's just go with the elements that make some sense, that we can at least see. All right, if you put a 0 in there, this would be March 25th. Good enough. Okay, so let's plug that in. We can plug that into ORSA. ORSA can accept two-line element format natively and put that into the program. So that's what I've done here. I've integrated forwards for 1 year at 1 minute intervals, and then backwards for 1 year from the moment of epoch. And the reason I did it starting at the moment of the epoch of the orbital elements is that if I started at any other point, it wouldn't take into account the gravity of the planets between the point that I started and the actual epoch of the elements. But by starting at the epoch, we can see directly where this object supposedly came from and where it's supposedly going for any given point in time. So again, I've integrated forwards and backwards 1 year from today, and then I integrated forward 37 years with a 1 day time period interval. We'll start off here with the forwards 1 year with 1 minute time intervals for the integration, and just see what it looks like. So again, this starts on March 25th at the epoch of the orbit itself, and if we center up here on Earth and zoom in, you can see right away just how highly elliptical the orbit of this supposed asteroid is. In fact, it's gigantic. Let me zoom all the way in here so you can see how wide the moon's orbit is by comparison. It has nothing on the semi-major axis of this asteroid's orbit. Now that actually means this asteroid is way outside the Hill sphere of Earth, or at least it gets to be outside the Hill sphere of Earth. In other words, Earth's gravity can't hold on to it. The gravity of the planets and of the Sun will dominate compared to Earth's gravity. So you're going to see that the orbit changes drastically in a very short period of time. I'll play it forward here, and you see time is going forward 1 minute intervals on the integration, and you can see how rapidly expanding this orbit is. Now at this point, it's already almost 1 on the eccentricity, so it doesn't take very much for the apogee distance to increase dramatically, and pretty soon it will break altogether. It will go greater than 1, and now it's in a solar orbit. It actually is orbiting the Sun, not Earth. And so if you play it even faster and you just see where it goes over the course of the year, it gets farther and farther from Earth. Okay, so that didn't hit us on March 25th, at least not after the epoch of the orbital elements. Let's see what happens if we go back the other way. Alright, so close that. We'll go backwards 1 year. So we'll assume that, okay, maybe they posted these elements and they actually meant that the impact occurred before the epoch of the elements. That doesn't make much sense, but we'll give them the benefit of a doubt. Zoom in on Earth. Okay, so going the other way. Backwards in time. You can see it contracting there. The asteroid's actually getting closer to Earth at this point. In the previous simulation we saw, it was actually already past the point of perigee, or the point that it's closest to Earth. Now it's heading back into perigee because we're going back in time instead of forwards in time. So I'll just go ahead and speed this up right along here, and we can see it contracts all the way down there to being almost circular. But again, it's still outside the Hill sphere of Earth. It's got an orbit much bigger than the Moon, and Earth's gravity can't hold on to it at that distance. So it starts to expand the other way. And it goes back into a solar orbit again. And it gets further away from Earth again. It never hits Earth. So whoever decided to create these orbital elements didn't do a very good job, because it doesn't even describe an asteroid that hits Earth. So, okay, does it ever hit Earth, at least any time in the foreseeable future? So I integrated forward to the year 2050, and I'll just show you what that looks like. Once it goes into a solar orbit, here's the orbit of the asteroid here. It's pretty stable, really. It doesn't change much. Okay, so did it ever hit Earth in that period of time? So we can graph out the distance of the asteroid from Earth. And we want distance. Connect the points. Here we go. So starting on March 25th, that's actually the closest it ever gets, which is still about 2.5 million kilometers. The next time it comes close to us, it's at about 11 million kilometers or so. And the next time it gets even further away, about 15 million. Next time it gets a little closer, but still not as close as it was this year. We're looking at about 5.9 million kilometers. And that's all it does. It never hits Earth. So whoever did this did a very poor job. They didn't even come up with elements that describe an Earth-impacting object. So, as they say on GLP, doom off.